This is your video for 8.2 areas in the plane. So area under the curve has been the main idea behind integrals that we've been working with now for a couple of chapters. But in many cases, it's useful to know the area between two curves rather than just the curve in the x-axis like we've been working on before. So that's what this is going to look like, how to find the area between two different curves. So some of our questions are going to look like the figure that we have drawn here between f of x and g of x. So if f and g are continuous functions and f is greater than or equal to g throughout your interval a to b, then the area between the curves is going to be the integral from a to b of f of x minus g of x. So it's always going to be the top minus the bottom. Now you may have questions where one curve crosses, like one curve starts on the top and then it ends on the bottom. In that case, you would just split it up into two different integrals. So you would just have to find the place where they intersect, do one integral for the first one integral for the second one. You could also, if you had a calculator, you could do absolute value between the curves, because then it wouldn't matter which one is on top and which one is on the bottom. So here's our first example. We're going to find the area of the region between the two curves given below, and we have the given bounds from 0 to pi over 4. So the first thing that you need to determine is which curve is on top and which one is on the bottom, and if they change position. So if one starts out on top and ends up on the bottom, or vice versa. So if you actually look at secant squared and sine of x, only on the interval from 0 to pi over 4, secant squared is always going to be on top, and sine is always going to be on the bottom. So our area is going to be the integral from 0 to pi over 4 of secant squared x minus sine of x, and then dx. And then we would go through and find our antiderivative and plug in our 0 and our pi over 4 using fundamental theorem. So this is going to be antiderivative of secant squared is tangent. Antiderivative of minus sine is plus cosine. And then again, I'm evaluating from 0 to pi over 4. So that is going to be the tangent of pi over 4 plus the cosine of pi over 4 minus the tangent of 0 plus the cosine of 0. Tangent of pi over 4 is 1. Cosine of pi over 4 is the square root of 2 over 2, or 1 over the square root of 2, whichever you want to use for that. The tangent of 0 is 0. The cosine of 0 is 1. So this is 1 plus square root of 2 over 2 minus 1, which is just square root of 2 over 2. So the area between these two curves from 0 to pi over 4 is the square root of 2 over 2. And my label would be units squared because it doesn't tell me centimeters or meters or anything like that. So you would just use the general units whenever that happens. Sometimes they're not going to tell you where your bounds are, but it does say for this one, find the area of the region enclosed by the two equations. So in that case, you actually want to see where the intersection points are, and those are going to become your limits of integration. So I'm going to go ahead and graph both of these equations so we can see where they cross. We can use some algebra to confirm that as well. So the y equals negative x that is going to cross at 0, 0, negative 1, 1, 1, negative 1, because it's this line that's coming down through here. So that's the line. The y equals 2 minus x squared, that's really negative x squared plus 2. So that is going to have a vertex at 0, 2. When I plug 1 into that equation, I'm going to get back 1. When I plug in 2, I'm going to get back -2, so that actually crosses there. When I plug in -1, I get back 1, so that crosses there. And so that quadratic looks like that, and that gives me my 2 intersection points. So I have an intersection point of x equals -1 and an intersection point of x equals 2. Notice that the quadratic curve is always on top between those two bounds. So that's the region that I'm looking at the area of. So when I set up my integral, it's going to be the integral from -1 to 2 of 2 minus x squared minus -x. You will have to be careful with your parentheses because if these had been switched around, you would have to make sure you were subtracting the entire quantity of 2 minus x squared. One of the biggest problems that I see students make in this section is just mixing up their negative signs and not carrying negatives through the entire way like they should be. So because I am going to integrate this by hand, I'm going to go through and simplify this. So this is going to become 2 minus x squared. And actually, I'm going to rewrite this so that I have my quadratic term first. So I have -x squared plus x plus 2 is going to be what I'm integrating. So antiderivative is going to be -1/3 x cubed plus 1/2 x squared plus 2x, and then we're evaluating from -1 to 2. So I have to go through, plug in my 2, and then plug in my -1, and simplify. So we have -1/3 times 2 cubed plus 1/2 times 2 squared plus 2 times 2 minus -1/3 times -1 to the third plus 1/2 times -1 squared plus 2 times -1. And then you have to go through and do the algebra on this. So 2 cubed is 8 times -1/3, that's -8/3. 2 squared is 4 times 1/2 is 2. And then 2 times 2 gives us 4. Let's fix that up a little bit. -1 cubed is -1 times -1/3 is +1/3. -1 squared is 1, and then times 1/2 is 1/2. 2 times -1 then is going to be our -2. We have to go through then and simplify this. You would combine these together, and when you do that, you actually end up with 9/2. And again, this is going to be units squared. So 9/2 units squared is going to be the area between these two curves. And you can double check this with geometry. 9/2 is 4.5. So you can see that that is reasonable with each tick mark representing 1. You can see you have a box of 1 and a box of 1 and then some partials. So this does actually make sense in the context of the question. So example 3, and this one brings up another way that we can possibly use these, and I've seen this type of question appear in the AP exam in the calculator section. We're going to be using the calculator on this one. It says find the area of the region enclosed by the graphs of the functions given below. So y equals 2 cosine of x and y equals x squared minus 1. Now you may not be able to tell which one occurs on top, which one's on the bottom. It also doesn't tell me what I'm integrating in between, which is the bigger problem. So I'm actually going to put these into my calculator. So I have 2 cosine of x as one of my equations. And then I have x squared minus 1 as my other equation. So I'm going to take a look at the graph of that, and I know the graph is already there. And you can see that, let's see here, it is a little bit behind where it's supposed to be. Okay, that looks a lot better. The middle screens here are a little bit behind. So you notice that one graph did not look like it had a straight line in there. So you do want to just have a little bit of patience with this new program. But my graph over here on the right-hand side, that gives me a really great picture. So the blue line was my cosine. The cosine is always on top, and then the red quadratic is going to be on the bottom. So I do know that whenever I set up my integral, whenever I set up this integral, the cosine is going to have to be on top. And then the quadratic has to be on the bottom. Now, the other issue is, where do these lines intersect? We are going to have to calculate that. So I'm going to press second trace. I want to go down to number 5, which is my intersection. So there's my first curve, second curve. And there's my intersection. So one of my x values is going to be negative 1.265424. You can either type that in, or you can actually store that as one of your variables. So we are going to actually use the calculator to calculate this integral, because it's not something we can do by hand. But I am going to write that down. Negative 1.26542237. And then if we go and find the other intersection, again, I want number 5. We'll be coming over to this side. And there's the other intersection. So it's actually the same value, it's just the positive version. So when you're setting up your integrals, you can actually put those numbers in, or you can store them as A and as B. Now, this will only work if you actually go to your graphing calculator and store them. I don't know that it would necessarily save you a whole lot of time if these were the only ones that you had to do. But if you had to do multiple questions over and over again, it could be useful to store those. So, I need to calculate my integral now. So I have my math 9. I'm going from negative 1.2654237 to 1.2654237. Make sure those match. And then I have to type in my equation. You want to make sure that you do put, well, you already have the parentheses around the whole thing. So I have my 2 cosine of x there, close that parenthesis. But then I'm subtracting, and I need to open up a parenthesis because the term that I'm subtracting has more than one term in it. So unless you want to distribute the minus, you do need to make sure that you say, okay, I am subtracting the entire quantity of x squared minus 1. And then, of course, my variable of integration is going to be x. And there is my solution. For the AP exam, you do it around to 3 decimal places. So this is going to be equal to 4.995 units squared. this is the last one we're going to cover in this video, and then the other examples will be in your video for part 2. And this is a problem that we're going to be looking at a couple of different times. So this is going to be our basic straightforward one. We're going to we are going to find the area between the curves using traditional method. Now, you do have to be a little bit careful with this, and you'll see why once we graph this. So, y equals x squared. Let's see, 1, 2, 3, 4. 1, 2, 3, 4. So y equals the square root of x, not x squared. At 0, we're at 0. At 1, we're at 1. 2 is going to be decimal. 3 is a decimal. 4 puts me up at 2. So there's the area, or the first curve there. The second curve, x minus 2, at 0, we are actually down at negative 2. So I'm going to extend this a little bit. Notice the curves don't intersect yet. At 1, I'm at negative 1. At 2, I'm at 0. 3, I'm at 1. And then at 4, I am up at 2. I know that's not perfect, but that's going to be the way that we work with this. So, it says we want to find the area of the region R in the first quadrant that is bounded above by y equals the square root of x and below by the x-axis and the line y equals x minus 2. So I'm looking at this area. Notice it does not say just the area between the curves, because when you look from the region from 0 to 2, the bottom boundary is the x-axis. However, whenever I move beyond that, I'm looking at the square root of x minus 2. So we actually need to split this up into 2 different integrals. The first integral is going to go from 0 to 2. And that is going to be simply the integral of the square root of x. You could subtract the x-axis equation from that, but you're just subtracting 0 from that, because the x-axis is the line y equals 0, so that doesn't really change anything. My next region then, from 2 to 4, has the square root of x on top, and then x minus 2 on the bottom. So it makes the most sense to split this up. Now we are going to go through, we're going to integrate both of these, and then we are going to combine them together. And there is going to be a little bit of algebra here. I may skip a few things, so if you do have questions, please contact me whenever you're going through this. So if I integrate this first one, the square root of x, remember this is the same thing as x to the 1/2 power. This is going to be 2/3 x to the 3/2. That one is being evaluated from 0 to 2. The next one, when I integrate, this is going to be a minus x plus 2, so that's what I'm going to use there. This is going to be 2/3 x to the 3/2 minus 1/2 x squared plus 2x, and then that one is going to be evaluated from 2 to 4. So, plugging in now. If I plug in the 2 here, I get 2/3 times 2 to the 3/2 power. If I plug in the 0, that's just going to be 0. I will write it out there, but that's actually gonna disappear. And then I have to plug in my 4. and plug in my 2. So with 4, we have 2/3 times 4 to the 3/2 power minus half of 4 squared plus 2 times 4. And then minus plugging in the 2. And I'm actually going to have to write this down in this next line because I'm running out of space here. 2/3 times 2 to the 3/2 power minus 1/2 times 2 squared plus 2 times 2. When you go through and do all that simplifying, you'll notice that you end up with a 2/3, 2 to the 3/2, and this is actually going to be a minus 2/3, 2 to the 3/2. So the nice thing is that those are going to disappear. You do have this 2/3, 4 to the 3/2, so that one will end up having a fraction in it. But when you go through and simplify all of this, you end up with 10/3. So much easier answer than it looks like it would be whenever you actually go through and do the geometry on that. And again, you can eyeball this area, and 10/3, 3 1/3, that is a very reasonable solution for this type of question. So that's going to conclude our first video for 8.2, areas in the plane. We are going to continue with this, looking at integrating with respect to y, looking at geometry, looking at going through and doing some of these questions in a slightly different way. So go back and rewatch this video and reach out to me if you have any questions at all.